But you have to be careful about how you measure the force, because you have to take into account that these are going in different directions. So the distance is going to be the magnitude of d, the length of this vector. But then the force is going to be F times cosine of theta, where theta is the angle between the force vector and the displacement vector. So if you take that angle into account, then this is the actual amount of force that's being applied to the object. So if it's dead on, then it's going to be the full magnitude of this force. But as this angle gets closer and closer to 90 degrees, no matter how much force you're applying in whatever direction, there's actually very little force that's being applied to the object. Yeah. So we have the magnitude of force vector, magnitude of distance vector times the cosine of the angle between them, so it's just F dot d. So in this case, the dot product of force and distance vectors is what gives you work.
Right.
Yeah. Okay. So now we want to use this idea for computing the work done to push an object along a curved path, where now the force is described by a vector field rather than a scalar valued function. So the force is being applied in whatever direction and magnitude. That's not necessarily the path that the direction that the object is going in. So once again, we have our curved path. So our object is moving along the path, but the force is a vector field. Let's say it's going this direction, something like this. So here's your force, F of x, y. So for every point x, y along the curve, we're getting some sort of force that's going to vary.
Okay, so the force varies, the path varies.
Yes, everything varies now.
Great.
So what you're doing, to try to figure out what that would be, is like before, we're approximating the curve by line segments. So now along each segment, the work, so we have n segments. So if we work along each segment, we're still going to fall back on this. So it's going to be the force evaluated at some point on the segment, dot product with, and then we're going to have the displacement vector. But what we're going to use for that is the unit tangent vector. And keep in mind, it's very important to say unit. So it's a normalized tangent vector. So all it's conveying is the direction of a curve. That's all we're looking for. And then for the length, we fill in the length of a segment, which is the same as what we had before. So we're applying this formula for work on each segment to get the work done to move the object along that segment. And then we're going to add all these up to get the total work, and then we're going to let the number of segments go to infinity. So then it goes to infinity. What we get from the work is, it's written this way, F dot t ds, where t is again the unit tangent vector, and we're integrating with respect to the arc length. So ds conveys the length of infinitesimally small segment of the curve. And if c is parameterized by a function r of t, a vector valued function of t, which gives you x of t, y of t, then this integral, f dot t ds, is also written this way, the integral over c of f dot dr. Now, so this is also a line integral of a vector field. Okay. Over a curve.
Is that C is parameterized by R vector too?
Yeah, parameterized by a. Yeah, so over here, what I'm doing is I'm using the same kind of parametric equations as before, x of t, y of t, but I'm bundling them into this vector r. And the reason why.
It kind of looks like a gamma.
Yeah, it looks like a gamma.
Oh, wait, where?
The R.
Your R,
This?
it's kind of
Yeah.
squared off like gamma.
Oh, uppercase gamma. I was like, what? Why do you call it gamma? So I'm thinking like this. Okay. Yes, that's just plain old R. Okay. All right. Now, but still, we need a way of writing this integral in such a way that we can actually evaluate it. So the way we could do that is by looking more closely at what this represents and using our parameterization. So this is our parameterization of a curve. Then our unit tangent vector at any point on the curve is going to be the derivative of this vector valued function. That gives us the tangent vector. But then this is a unit tangent vector, so we have to remember to normalize it. So this vector indicates the direction in which the curve is going at any particular point. Okay. So that's one piece that we need. We're going to assume that our parameter runs from A to B for this definition of a curve. Okay. So now we'll start to fill this in piece by piece. So our line integral of our vector field, we'll write it this way, f dot t ds. So now we can at least fill in some of this. So we have integral from A to B, and then we have f, and we're going to evaluate f at r of t. We're going to use our parameterization because everything has to be in terms of t. Now we take the dot product of this with our unit tangent vector, r prime of t over the magnitude of r prime of t. Okay. So we're almost there. We still need to fill in what ds is. Well, ds is no different from what it was before. ds is the square root of x prime of t squared plus y prime of t squared dt. But this is the magnitude of a derivative of our parameterization of our unnormalized tangent vector. So now we can replace ds with this. Okay. Cancel.